Uh, Question one. Consider we have a kosher wire made of A as core and B materials as shell. A and B can form a complete solid solution after annealing at high temperature. 它们可以形成均匀的固溶体。在高温的时候，the intrinsic diffusivity of A is much larger than that of B. Describe how the AB composite wire morphology evolutions after annealing at a higher temperature for 4 hours. So the clue or the hint here is the intrinsic diffusivity of A is much larger than B. Based on Fick's first law, the flux equals to negative diffusivity concentration gradient. But concentration gradient for A and B, actually the concentration gradient pure A and pure B, so there's no big difference in concentration gradient. But the intrinsic diffusivity of A is much larger than B, so it implies that also according to Fick's first law, JA should be larger than JB. Okay, so let me have a quick draw here. Uh, so we have A here, A materials here, and B here. And as we know, JA is larger than JB. Okay, so based on net flux equals to 0 at any your interesting specific net plan, so we know that uh, it come out vacancy flux indoor. So you will observe some vacancy in A materials as time increase. I believe you will have more and more vacancies avoid. And here they give you 4 hours. Okay. So what's the question here is if the Y diameter of the Y in the range of hundreds of micrometer, tens of nanometers, and 1 to 2 nanometers, explain your reasoning in details. So they ask about the wire morphology evolutions. So it turns out it's time dependence，这是跟时间有关，对不对？所以然后他给你了 4 hours。So in the meantime, they also give you the diffusivity, the roughly diffusivity for this interdiffusion. Okay, so this diffusivity should be what? You can use this diffusivity to the diffusivity. Actually, you can check the slide we learned this in. So this is we call the interdiffusivity. So the diffusivity they given to you probably is interdiffusivity. Okay. So based on this idea, interdiffusivity. So you can use the interdiffusivity to estimate the diffusion length. So you can use the square root of 4d t. Okay. So t should be in seconds. So the result is around 75 nanometers. For you times the 10 to negative 19 times time. So 4 hours you times 16 in minutes, for minutes, then times 16 again in seconds, for seconds. So you will final you will get around 75 nanometers. Okay, so based on this, you know the diffusion length is around 75 nanometers. So compared to 75 diffusion length, compared to the diameter in hundreds micrometer, is quite large, right? So the morphology should be go like this. Because the diameter is up to hundreds micrometer, hundreds, right? So would be 1,000 larger uh, compared to the diffusion length. So the diameter is like larger. So the interdiffusion distance should be shown in green here. So I draw this is like we can observe some void formation in A materials due to the vacancy fluxes move inward. And the diffusion length, interdiffusion length is around 75 nanometers. So I draw like these thin layers to interpret A. We have diffusion in between A and B. But the diameter for this wire is 100 micrometers. So it can be shown like this. But if let's say the diameter down to tenths of nanometer is around like is in the same orders, so probably the 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 diameter is similar to the diffusion length. So I believe the interdiffusion, I mean, continue, even, complete. So I will have this like AB Harrow wire because the diameter for this is tens of nanometers, and for after 4 hours, the diffusion length is around 75 nanometers. It more or less is like this. But if the diameter down to only 1 to 2 nanometers, 1 to 2 nanometer means that like in probably within 30 minutes or less, we should like we should like we should have we will have like a less like AB Harrow narrow wires because in the diameter is only 1 to 2 nanometers, which means that within 30 minutes or less, the AB diffusions, I mean interdiffusion have complete. Then the rest of time, which means that the rest of around 3 hours, I believe this narrow wire will shrink. So in the beginning, the system will reach like will fast reach this narrow wires. Then the rest of time, this tube or this wire will shrink. So the size will decrease less than 1 nanometers. Okay, so this is for your reference. So the most important part is you need to estimate the diffusion length. That can help you to know after 4 hours what happens in different diameter of this wires. And we still have question 2 here. The question 2 here is consider we have a metal hollow ball. This is a hollow ball of inner radius 4 nanometers and the outer radius of 6 nanometers. And I will allow diffusions happens at 800 K is high temperature. And and then the question probably would be like can you tell me the diameter evolution after 4 hours or 12 hours at 800 K? So it turns out, as we mentioned, as if you continue heat these materials up at higher temperature, then due to this only one driving force acting on these materials, right, is curvature effect. So as we mentioned in prior slide, this hollow ball is going to shrink due to the, if you take a look, if you if you have like a point of view for the atoms with higher surface potential will move to inner surface due to at this region they have a lower surface potential with negative kappa, right? So this Haro structure will shrink. So if I ask you what can you tell me about the diameter evolution after like 4 hours or 6 hours at 800 K? What are you going to answer or how to start to answer? In order to know the total volume, how much the shrink of this total volume of this hollow ball, probably you need to know the vacancy flux, right? As we mentioned or as we talk about the similar idea, uh, for this one, in order to know how much time it takes to form this void, you need to we actually we starting from the JV. As long as we have JV, then we know how much time it will. So now, if you have the JV and you know the time, you also can estimate the total shrink volume of this shrinkage, right? So let's move to the questions, back to the questions. So in order to answer this type of questions, you need to calculate the JV, the vacancy flux here. Okay, so what is the JV? So I also provide the corresponding information here. We give you the vacancy, formation energy, service energy, which is gamma. Omega is atomic volume, and also give you some related information diffusivity for the copper and Maxwell Boltzmann constants and the EV, the relationship between EV versus the Joule. So what's a JV? Probably the first thing come out from your mind would be, actually we have learned that there's a vacancy concentration variations, and we even know the equations shown in previous slide, right? Where so I can grab that to you. So it's here. You even know the concentration of vacancy as a function of kappa. So based on these results, we have chance to estimate. Sorry, we have chance to estimate the vacancy flux by the mobility, concentration, and the driving force. And the driving force here would be the gamma, omega, and kappa gradient. And but here is a vacancy. Okay, so this is the chance to get the JV. But if the question not just want ask you about they ask you not only ask you about what's a JV, they also ask you about could you please calculate the equilibrium vacancy concentration at inner and outer surface. So we will use the equation we have learned before. So this one actually is tell you the vacancy fraction is equal as function of kappa equals to exponential negative vacancy formation gives free energy plus the extra work we try to put the lattice point on the surface of this uh, materials divided by KT. And so the inner and outer, for inner, I just fill all the informations here. So vacancy formation energy is 0.92, but is EV. So we need to times the EV to convert this to jar. And we also plus the gamma. Gamma is surface energy is in jar, doesn't matter. And kappa, actually kappa is equals to kappa 1 plus kappa 2. And this is ball, right? So it's 2 divided by radius. So this is inner, so I put the radius is 4 times 10 to negative 9. And this is inner, so don't forget the sign for the kappa is negative. As we mentioned before, no matter you put the atoms or vacancy on the surface, the kappa should be positive for the convex region. But for concave region, no matter it's atom or vacancy, should be negative. So we'll put a negative here. And omega is average atomic volume, just copy here. But don't forget to convert it into meters. And the bottom should be K. I put the K here. And don't forget this is EV, so converted this into jar. So the same idea to deal with the outer one. So due to I have XV and based on the if I ask you about the concentration, so should be converted to concentration by divided by the average atomic volume. So you will get the CV inner and CV outer. But after simply calculations, and you will image that the inner concentration should be larger than outer because you can see this minus this one, so you got smaller exponential smaller term. You get a larger XV for inner, but after roughly calculation, the XV is around. I can give you some values for my roughly calculation. 4.2 times 10 to minus 6, and the outer should be 8.3 times 10 to negative 7, just for your reference. Okay, so based on we after this calculation, we can double check the concentration. For vacancy inner will be higher than outer, so the vacancy flux will move outer. So you got more vacancy at the surface, so this will be shrink. Okay, so narrow ball shrinking after like you hit this materials up to 800K. And we already answered, but we haven't answered the JV, right? So you can use the mobility concentration and driving force. And driving for mobility, just copy, and the concentration variation. Concentration should be you take the average for the inner and outer surface CV for for inner and outer surface. Take the average for CV for inner and outer. So take the average for this one, and gamma is gamma, omega is omega. The other one easy to confuse will be kappa gradient, kappa V gradient. So usually the vacancy will be go this way, right? So usually I will use this to minus this one. So positive minus negative. So and the gradient will be the thickness for this one is 6 minus 4 nanometer. So you convert it to meters times 10 to negative 9. Okay, so this is for reference. So so now you know the JV. So even I ask you like how about after like 12 hours? What's the diameter for this horrible? I believe you can estimate. Okay, so for reference. So let's move to the fifth section. We talk about the stress migration. Stress migration, which means that the stress field induce atomic migration. So we will first of first part we will talk about the stress dependent chemical potential. Due to we have stress field, so this stress uh, will cause the difference in chemical potential. We got the potential term will be difference due to we have compressive or tension stress. So this mass transport driven by stress gradient. So you need to learn how to express the compressive and tension stress and how to calculate the stress gradient. So before we take this more in details, we will show we will show you an example to demonstrate that the stress gradient does induce the atomic migration. So what we have here is we have the candle on the gas stove. So we've tried to fill the water inside the candle and put it on the gas stove to heat this up. Initially, the candle shows no sign of deformation. But however, once all the water evaporated, the candle become distorted. So this is the common sense or common phenomena we observed, right? As long as water totally evaporated, then you will get distorted candle. So what's the mechanism behind here, this phenomena? So this is the wall of the candle, and when you try to fill the water, and I put the water inside. When you try to heat this candle filled with water up, then you will get a temperature gradient. The outer usually have higher, and the inner due to the water, so you have a colder side. So the wall suffering a temperature gradient. So if the heat of transport is positive, the atomic flux driven by this temperature gradient will be pushed to inward or pushed to left-handed side. But at this moment, you still have water, right? So, and this water would start evaporating. So you will gas the water vapor to push this wall. So you will get the stress gradient. This water vapor will induce atomic flux. So at this moment, you are not going to visualize or see the distorted candle until what? Until this driving force disappear, which means that the total water be evaporated. So only this driving force. So you will get, as long as the candle dry out, then you will get the distorted candle. This is the reason. Oh, this is the typical example demonstrate that the stress field induced atomic transport really happens. Okay, even in your daily life. So in order to quantitatively analyze this atomic flux driven by the stress field, so we were starting from some potential term. So mass transport under stress gradient, which you also some people call it as a stress migration. So consider we have the interstitial cause a pure dilation omega, delta omega. The chemical potential becomes what? This is potential term, right? And before we don't have stress field, then the potential was mu1. But you need to modify by extra term due to you you have interstitial cause of pure dilation. So what this means? Before we have interstitial, the atoms show like this with the same distance in between. But however, now you put the interstitials, then you you push the interstitial in between these host atoms, and that will cause the compressive region here, right? So you put this interstitial, you insert this interstitial into this crystal, which means that you deliver the work. So now the atoms have higher potential compared to it was, right? Before you don't have it, we call it mu1, but when you insert this one, so the atoms have higher chemical potential. But how high it is should be ended the extra term. So here we know that if the atom stay in compressive region, which will just deliver the work into the system, so the potential should be larger than mu1. So in compressive region, they have the P, actually they use the stress. Compressive region, the P is negative because negative, you got a positive, you got ended extra term. So you will have a chemical potential higher than it was. So negative P delta omega, then omega. So how to remember this term? As we mentioned, potential term. Potential term is you can consider as stress times the volume. Why? Because is stress is force divided by area. So you times the volume, so you got the force times the distance. So this is a work. The unit is work. So it's perfect with potential term. So mu negative minus the stress times average atomic volume. So we call this is the extra term for modification term for stress gradient. But on the other side, or on the contrary, in the tensor region is the upside, is the other case, right? The P will be, you can consider as positive. So we have, as long as the atoms at the tensor region, it has a lower chemical potential compared to it was. Okay, so it turns out the atoms always move from higher potential side toward to lower potential side. So as we learned before, this explains why the atoms move from compressive region toward to tension region. Because in compressive region here, the atoms have higher potential compared to tensor region. Okay, and so the atoms move from compressive region to tensor region, but if you switch to vacancy point of view, vacancy will flow in upside direction, which means that from tensor to compressive. So now the most important part will be the atomic flux here also can be written as two terms. The first term is due to fixed first law, due to if we have a concentration variation for these interstitials. And the second term will be mobility, concentration, and the driving force. So it's the same idea what we told you, right? Your driving force is negative potential gradient. So you just fill this into substitute this term. So we can write down the first term is obey fixed first law, and the second term negative and positive. So we got the mobility, concentration, and driving force. Okay, mobility, concentration, and driving force. Okay. Okay. Mobility, driving force. Driving force is the average atomic volume times the stress gradient. So in order to interpret more or give you more pictures here, so I draw the figures. The vertical axis is a stress, and I put a 0 here. But because, as we mentioned, compressive region means we have negative stress, and tensor region we use T to means that we have positive stress, and the x-axis is the directions, because we always deal with a gradient, right? Okay, so now if I assume the atomic flux is moved to right-handed side, okay, then if we just ignore or we assume this interstitial variation is quite small, so based on these equations, we know that this is positive, 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 right? So move to right-handed, this is positive, so the stress gradient should be positive, so it should be deng, 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 right? So this tells you that the atoms probably will move to high compressive region toward to low compressive region. Or the atoms can move from low tension to high tension. This is the low tension. This is high tension, right? And compressive region to tension region. So these three cases can well describe. If you visualize the atomic flux for these interstitials move to right-handed side, then there are two possibilities for this where these atoms, these interstitials move from where and to where. Okay. So now we give you like two examples. Here is under what kind of conditions in materials you will visualize this kind of stress gradient besides the dislocation. Okay, so what we have here is we have polycrystalline materials, and this material suffer with the shear force. So we have a tau here, and tau downward and upward. And this tau actually can be dissociated into two folds. This is compressive to this this grain, and all the tensile So compressive tensile, let's sum these two factors together, then you can get the tau. So here, compressive means that the A tensor will move from compressive region toward to tensile region. So this blue vector or arrows point out where the A tensor moves. So A tensor move from compressive toward to tensile. Also, compressive move to tensile. Why this tensile? Because the tau is here, you can dissociate into compressive and tensile to this grain. So compressive to tensile, compressive to tensile, compressive to tensile. So you can use these blue arrows to indicate where the atoms moves. Okay. So so chemical potential gradient is, as we mentioned, will be average atomic volume times the stress. And this actually is the one you have learned in metallurgy. We call it diffusion creep, the mass transfer from compressive region toward to tensile region induced by stress gradient. And if you switch your point of view to the vacancy, then everything will be in upside directions. The same, everything are the same, but we use the purple arrows to demonstrate that the vacancy, the moving direction for the vacancy will be go the upside directions. So you can see that from the tensile to compressive, the tensile to compressive, tensile to compressive, tensile to compressive, just for your reference. So the vacancy flux is from tensile to compressive. Okay, so this is for how the stress gradient um, changes the morphology evolution in polycrystalline materials. But if we give you the other examples, what we have here is we have edge dislocation inside these materials. And we also have a dopant, interstitial dopants. And due to you have edge dislocation, so that will lead you have this region is compressive region. Compared to this one, the bottom will be tensile region. So this stress gradient will induce the interstitial, the migration of these interstitials. Why? This is because have compressive region have a higher, because it's negative, you mu1 plus extra term have a higher potential. So and tensile region, the P is positive, so you minus a positive term, so you got a smaller chemical potential. So at this region, interstitial have higher chemical potential compared to tensile region. So this interstitial tend to move to the tensile region. Okay. So in order to quantitatively interpret this phenomenon, your textbook give us an example showing here. What we have is diffusion of interstitials in the stress field of dislocation. So we hope you can have interpret the equilibrium concentration distribution for these interstitials. So we assume that the interstitial concentration is maintained at a concentration C0 far from the dislocation. This is like give you some boundary condition, which means that the dopant concentration for these interstitials are at C0, which is far away from the dislocation. And the questions here will be, can you write down the CI, the concentration of these interstitials as a function of stress P? So we need to think about that. When a system reach quincy steady state, which means that the net flux equals to 0. So we need to image that how many possible driving force to induce this atomic flux. Probably think your mind will be two, right? The first one is concentration of this gradient of this interstitial. The second one probably is the stress-induced atomic flux should be equals to 0. So this is how you should write down. So the first one is due to the concentration variation in these dopant interstitials. The second part is stress field induced term. So it will be mobility, concentration, and the driving force. Okay, driving force here is omega average atomic volume times the stress gradient. Okay, but this turns out complicated. It is difficult to you to move forward because you have two terms, right? But you need to write down the total concentration of this interstitial change with stress. So, but we visualize two gradient terms. So one way is, how about I combine this simplify this combine these two terms into one terms into gradient term. So I just do the thing. I just so I want to take this uh because I need to combine all this, right? So the first thing is I just try to gradient. I find which if you gradient what extra term you will get the gradient C1. So I try to put the C1 inside the gradient term. So I find that log C1, you gradient log C1, you will get the 1 divided by C1, gradient C1. So you put a C1, so this is equal. So I can just use this to substitute this term. And then the second is I take the C1 outside. So I got the omega kt gradient and gradient here P. So this term, so it was two terms, so I combine them into one terms. So this is just mathematical trick. 这只是数学的 trick，把两个 gradient 完全不相干的 gradient，然后放在一起。那为什么他会这样做？Why should I go this trick? Because net flux, I have a boundary condition for quincy steady state. Net flux equals to 0. So if I can combine them one into one term, the gradient term should be equals to constant on when the system reach quincy steady state. 这就是原因。因为我如果把它 combine 在一起的话，我有这个 boundary condition 是 quincy steady state 的时候，这个会等于0。那这个等于就是表示 gradient 里面它不会随着距离而改变，它是个常数，所以我就有机会求出 C1，这就是一个 trick，好不好？然后接着就是因为我用这个，所以这里面会等于 constant，所以然后接着我再带 boundary condition，这里会是 constant，但我想知道这 constant 是多少，所以我就可以带说，当它远离 dislocation 的时候 ，stress 是0的时候，A 就等于 log C0。哦，因为这个时候 C1 等于 C0，所以 A 就等于 C0，所以我就把这个带进来之后，那我就会求得 I can get this C1 equals to C0 exponential omega divided by KT times P. Okay. Okay, so how to get this? Because you know this is log C0, right? And this you move to right-hand side. And log C0 you move to left-hand side. So you use the explanation term. So you got a C. So you could get this result. It's a quick and simple calculations. So next, as long as you not get this results, the concentration of interstitial equals to C0, which is the C0 is a concentration of dopants far away from a dislocation. Then you times the explanation and average atomic volume divided by KT times P. So here we know that if in the compressive region, P is negative. So you got the C1 will be smaller than C0. Yes, because more interstitial move to tensile region. So afterward, you will visualize more interstitials observed in tensile region than in compressive region. So I'll give you a quick summary for the capillarity and stress field induced migration. For capillarity effect, the original it actually is due to the finally will reach the surface planization. And the driving force here is due to chemical potential difference due to the surface curvature. The atoms always flow from convex region with higher service potential move to concave region with lower service potential. Then to my personal uh, habit is I use kappa, positive kappa for convex and negative kappa for concave. And for stress-induced atomic migration, also due to the chemical potential difference. And how to modify them is also the extra term, stress times average atomic volume. And to my personal convenience or habit, due to uh, atoms at compressive region have higher chemical potential. So compressive region, P is negative. So negative, negative, positive. So this is extra term to increase the chemical potential. Okay, for the compressive region. So as we mentioned that the after war, the atoms always move from compressive region toward to tensile region. So after that, you will observe the more concentration of interstitials in tensile compared to compressive region. And the atoms flow along the directions of stress gradient, which means that along from the compressive to tensile. So some people don't understand this. This is the atoms moves from along the uh, which means that along the stress gradient, because this minus this one is positive. You use a positive term to minus a negative term, so you will get the positive. So positive is moved to right-handed side, the same direction as atomic flux. So which means they means the along. This small negative minus a larger negative, so you also get a positive. So this is why they mean along. Okay. So atomic flow along the direction of stress gradient. Okay. So we this is all we ended here. So we close the lecture 2.